It happened on a night when the sky should have behaved like a laboratory. On October 22nd, 1966, satellites and sensors in orbit were trained to watch for something very specific: the faint, telltale fingerprints of a nuclear test. In the middle of the Cold War, the world had agreed on a blunt logic. If a thermonuclear device detonates in space, it will leave behind a signature flash energy radiation patterns and a burst that can be traced back to a point in the dark. Then, the Vela satellites reported something that looked uncomfortably like exactly that in the official wording that followed. The event is often described as a double flash. Two bursts, separated by a fraction of time, appearing to come from nearly the same place above Earth. The interval mattered. In theory, it resembles the sequence expected when a high-energy detonation produces an initial gamma-ray flash, and then, after interactions in the upper atmosphere and magnetosphere, a second bloom of radiation. But the mystery wasn't just that a flash was detected. It was that multiple lines of evidence didn't line up cleanly. The instrumentation was designed for early warning, not detailed forensics. Still, the data had enough structure that some engineers and analysts believed they were seeing an actual nuclear event. Others pushed back, arguing that the sensors could be fooled by cosmic rays, by lightning far above storm clouds, by reflections or geometry effects that turn a real particle event into something that resembles a controlled signature. What is striking is how quickly certainty becomes complicated. The official summary leans toward the simplest narrative. A Vela satellite detected a nuclear test, but classified details and later assessments muddied the trail. The record ends up full of institutional caution enough to signal responsibility, not enough to satisfy an honest forensic question. Even for a classified program, you would expect a clear accounting of calibration, background rates, and why alternative explanations were ruled out with confidence. Instead, what survives publicly is fragmentary, and the gaps are not small. Consider the geometry. Space detonation signatures are not just flashes. They imply specific locations relative to Earth's magnetic environment and the atmospheric path that the radiation takes. The Vela anomaly was associated with a region where charged particles and auroral processes can complicate readings. If a natural high-energy event can mimic some parts of the signal, then the remaining pieces become critical, and that's where the public documentation is thinnest. Some researchers argue the radiation spectrum and timing resemble a nuclear source. Skeptics counter that the same patterns can be produced by intense non-nuclear processes under the right conditions. Meanwhile, there's a human element that still feels like a missing page. The internal debate reportedly ran through the late 1960s and beyond, and later recollections differ on what was considered good enough to label the event a test, when even those closest to the data can't agree on the interpretation. The official explanation starts to look less like closure and more like a decision made under constraints. The Vela incident becomes a paradox, a detection system that was built to be precise, producing an output that is compelling enough to alarm, yet ambiguous enough to never fully settle. And that is why people still argue about it decades later. Not because they deny physics, but because the evidence is shaped by what the record chose to preserve and what it chose to withhold. The sky replayed an event that looked like a thermonuclear flash, but the reasons to believe and the reasons to doubt were never presented with the completeness the stakes demanded. The next question is not whether something flashed, but what kind of event could write a signature so nuclear-like and still leave the door to other explanations slightly ajar. When people hear signal, they picture a clean message arriving intact. But instruments don't work like that. They turn photons, particles, or radio waves into electrical traces, and then into decisions. The trace is the raw material. The decision is where confidence can be manufactured without anyone intending to lie. In the Vela case, multiple channels watched the same sky. Yet the argument centers on how those channels transformed uncertainty into a conclusion. One first comes the threshold problem. A sensor can only be said to detect something if it crosses a preset line, a certain count rate, a certain pulse shape, a certain timing relationship across detectors. Below that line, the same physical phenomenon may exist, but gets classified as noise or routine background. Above it, the system flags an alarm and locks in an interpretation pipeline that favors the most dramatic fit. That is not fraud, it's design. But design can steer what later analysts think must have happened, simply because it triggered the system at all. Then comes the processing step, where ambiguity gets compressed. Data is rarely kept in full resolution. It's filtered, binned, and compared against reference templates. A nuclear-like event would be expected to produce a particular time, evolution, fast rises, characteristic decay, and correlations between channels. Yet templates are assumptions dressed as mathematics. If an intense, non-nuclear source shares enough of those statistical features, the pipeline can still produce a confident label, especially when the event sits near the edge of what the filters were tuned to recognize. The public record often shows summaries rather than the entire decision chain. We see outcomes, flag detections, derived spectra, estimated times. What's missing is the why behind each transformation where the data was truncated, which calibration constants were used, and how borderline readings were treated. The same dataset could be made to look decisive or merely suggestive, depending on those choices. In other words, the dispute isn't only about what the sky emitted. It's about how the instrument's logic decided what was worth preserving. Two even thresholds and processing have an interaction with the environment. Detector performance shifts with temperature, aging components, and background radiation levels. A system that is precise on one day can be subtly biased on another, and the bias can hide inside standard-looking plots. Analysts then compare those plots to physical expectations, sometimes with scant documentation of calibration drift or decision rules. That creates a gap. The more confident the plotted curve looks, the less visible the uncertainty becomes. So when investigators say we detected a nuclear source, skeptics don't just disagree on interpretation, they point at the path from signal to verdict. If the system's thresholds favored alarm conditions, and if the processing favored nuclear-like templates when the data was incomplete, then detection becomes an effect of the measurement strategy, not a direct reading of the underlying mechanism. Yet, if analysts tuned the system conservatively and still got an alarm that matched nuclear signatures, that too demands an explanation because it means the signal wasn't merely noise, it was compelling. This is the core dilemma. Instruments are built to produce answers, but space doesn't deliver answers in advance. It delivers scatter, overlap, and partial patterns. The question becomes how much of the conclusion was earned by the data, and how much was shaped by thresholds, templates, and the parts of the record that were never fully shown. And once you see that, the disagreement over Vela stops being only about what was seen, it becomes about which steps were allowed to count as the evidence. The next layer is where those steps are examined more closely, and where the timeline and methodology start to fight each other. Two Cold War space intelligence didn't run on a simple question like, is it there? It ran on a pipeline. Listen, classify, notify, and then crucially decide what could be written down. The universe offered weak signals and messy timing, while agencies offered rulebooks, thresholds, and cover stories. When later investigators try to reconstruct a puzzling event, they're not just missing facts. They're often missing the very reasons certain facts were allowed to survive in the record. The missing context matters because monitoring was designed to catch the improbable quickly. Early warning systems favored speed over perfect certainty. That means an output could be triggered by patterns that were close enough to predefined templates, then escalated before full confirmation was possible. In the documentation, you may find the alarm and the action, but not always the calibration notes, the intermediate rejections, or the internal debate about false positives. In other words, the record may preserve the moment of confidence while blurring the moments of doubt. And Secrecy didn't just hide results. It shaped the story that became official. Access restrictions determine who can compare datasets, who can question classification assumptions, and who can verify whether the processing chain was stable. If analysts later lose the raw telemetry or the excluded channels, the remaining evidence looks cleaner than it really was. The curve on a plot can become a kind of narrative, even if it began as a contested interpretation. The anomaly then takes on a second life, not as a measurement problem, but as a political or technological fable. Even within the intelligence ecosystem, Different agencies could observe the same phenomenon through different lenses. One system might emphasize high-energy signatures, another might prioritize timing consistency, and another might only record what crossed a reportable threshold. So when you read later accounts, you're often seeing the intersection of constraints, not the full space of possibilities. The official record ends where the pipeline turns into policy. That's why skeptics argue that an unseen component is doing the explaining. Not necessarily an alien technology, not necessarily a clever hoax, just the reality that the Cold War as monitoring culture treated uncertainty as a liability to be managed. If intermediate logs were downgraded, if some sensor modes were classified, or if certain calibration procedures were never public, then later observers inherit a partial image and have to infer the rest from shadows. So the question doesn't stop at what signal appeared. It moves to who controlled the criteria for declaring what the signal meant, and what parts of the process were permitted to be remembered. The mystery echoes because the documentation echoes back selectively, like a reply that arrives without the original question. And that brings us to the next layer, when the records narrow. How do we know whether the remaining fragments represent reality or a deliberately shaped version of it? So in the end, Space Mysteries Explained doesn't mean we replace the unknown with a neat answer. It means we track how the unknown gets processed. Sensors report slices, analysts inherit filters, and history preserves what policy allows. The anomaly is real enough to be worth chasing, but it's also shaped by the limits of what could be measured, recorded, and released, turning evidence into a kind of curated memory. If you want the fullest picture, don't just ask what happened, ask what was excluded. Watch the next evidence breakdown and leave your theory in the comments.